Identity matrix. To begin, let's understand the purpose of this matrix. In the world of matrix algebra, the identity matrix serves as the multiplicative identity. Now, that might sound like a technical term, but it is actually very simple if we compare it to the basic arithmetic you already know. Think about the number 1. In basic math, the number 1 is the multiplicative identity because any number multiplied by 1 remains unchanged. For instance, if you multiply 5 by 1, the result is still 5. The identity matrix performs this exact same role, but for matrices. It is essentially the matrix version of the number 1. Hello everyone. Today, we are going to introduce a fundamental concept in linear algebra called the identity matrix. In the upcoming slides, we will dive deeper into the formal definition, learn how to construct one step by step, and explore how it behaves during matrix multiplication. Definition of an identity matrix. Now that we have established that the identity matrix acts similarly to the number 1 in basic arithmetic, let us dive into its formal definition. First, it is important to understand that an identity matrix, which we will call matrix A, must always be a square matrix. This means it has an equal number of rows and columns, which we denote as n by n. In terms of its structure, all elements located on the principal diagonal, the line running from the top left to the bottom right, must be equal to 1. Meanwhile, every other element in the matrix, known as the non-diagonal elements, must be equal to 0. To express this more mathematically, we define the elements, a sub-ij, using a simple rule. The element is equal to 1 if the row index I is equal to the column index j. However, if the row index I is not equal to the column index j, the element must be 0. To ensure this is clear, let me explain the indices. The letter I represents the row index, and the letter j represents the column index. Therefore, when I equals j, we are referring to the diagonal elements, such as a 1, 1, a 2, 2, or a 3, 3. When I does not equal j, we are referring to all the positions that fall outside of that main diagonal. With this formal definition in mind, we can now move forward to look at the specific notation used to represent these matrices. Notation of an identity matrix. Now that we have established the definition and the structure of the identity matrix, let's discuss how we represent it using mathematical notation. First, when we want to specify the size of the matrix, an identity matrix of order n is denoted by a capital letter, I with a subscript, and this subscript is very important because it tells us exactly how many rows and columns the square matrix has. However, in many mathematical problems, the size of the matrix is already obvious from the surrounding information. In such cases, we can simplify the notation and simply denote it as a capital I. Understanding this notation is essential, as it allows us to move forward to the next section, where I will show you the step-by-step process of actually constructing these matrices. Step-by-step construction of an identity matrix. First, you must create a square grid. This means you need to ensure that the number of rows is exactly equal to the number of columns, resulting in what we call an n by n matrix. Second, we fill the principal diagonal. You will place the number 1 in every position where the row index is equal to the column index. To put it simply, this means placing 1s in the positions for row 1 column 1, row 2 column 2, and continuing this pattern all the way down to row n column n. Finally, you fill the remaining space. Every other position in the matrix that does not fall on that main diagonal must be filled with the number 0. Now that we have covered the definition and the notation of the identity matrix, let us walk through the actual process of constructing one. By following these 3 steps, you can build an identity matrix of any size. To see this process in action, let us move on to the next few slides where we will apply these steps to create specific examples of order 2 and order 3. Example 1, identity matrix of order 2, I2. Now, let us apply the construction steps we just discussed to a concrete example. We will begin with example 1, where we create an identity matrix of order 2. First, following step 1, we create a 2x2 matrix, which means our grid consists of 2 rows and 2 columns. Next, in step 2, we identify the principal diagonal. We set the element in the first row and first column, a sub 1, 1 to 1, and the element in the second row and second column, a sub 2, 2, also to 1. For step 3, we fill the remaining non-diagonal positions. We set the element in the first row, second column, a sub 1, 2, and the element in the second row, first column, a sub 2, 1, both to 0. As a result of these steps, we arrive at the identity matrix of order 2, denoted as I sub 2. This is a square matrix where the top left and bottom right elements are 1, while the other 2 elements are 0. Having mastered the 2x2 version, we can now see how this same logic applies to larger matrices in the next slide. Example 2, identity matrix of order 3, I $3. Now that we have seen how to construct a 2x2 identity matrix, let us move on to a slightly larger example to reinforce the concept. First, in step 1, we begin by creating a 3x3 matrix. Remember, as we discussed in the definition, an identity matrix must always be square. In step 2, we focus on the principal diagonal. We set the elements a sub 1, 1, a sub 2, 2, and a sub 3, 3 all equal to 1. These are the positions where the row index and the column index are identical. For step 3, we simply fill all the remaining positions in the matrix with 0. This results in the identity matrix of order 3, which we denote as I sub 3. Looking at the final matrix, you can see a clear diagonal of 1s running from the top left to the bottom right, while all other entries are 0. Once you are comfortable with this construction, we will move to the next slide to discuss the real-world analogy of why this specific arrangement of 1s and 0s is so powerful in matrix algebra. Real-world analogy, the multiplicative identity. Now that we have learned how to construct the identity matrix for different orders, let's discuss why this specific matrix is so important by using a real-world analogy. Think back to basic mathematics. We call the number 1 the multiplicative identity. This is because any number multiplied by 1 remains unchanged. For example, 5 multiplied by 1 equals 5. In the world of matrix algebra, the identity matrix, denoted by the letter I, performs this exact same role. To put this into a mathematical property, if we have any square matrix, which we will call matrix A, of order n, then multiplying matrix A by the identity matrix of order n results in matrix A similarly. If we reverse the order and multiply the identity matrix of order n by matrix A, the result is still simply matrix A. This unique property is not just a theoretical curiosity, it is absolutely essential. It provides the foundation we need for more advanced operations, such as finding the inverse of a matrix and solving systems of linear equations, which we will explore further in our upcoming lessons. Relationship with other matrices. If you look at the first point on the slide, you will see a hierarchy. Think of this as a family tree moving from the most general category to the most specific. It begins with the square matrix, which then narrows down to the diagonal matrix, then further to the scalar matrix, and finally, the most specific version is the identity matrix. To explain this further, an identity matrix is actually a special type of scalar matrix. In a scalar matrix, all the elements on the main diagonal are the same constant value. In the specific case of the identity matrix, that constant, k, is exactly equal to 1. Finally, because every scalar matrix is, by definition, a diagonal matrix, since all elements outside the main diagonal are 0, it follows that the identity matrix is also a diagonal matrix. Now that we have seen how to construct the identity matrix and understood its role as the multiplicative identity, let's examine how it fits into the broader classification of matrices. Understanding this relationship is important because it helps you categorize matrices correctly, which we will summarize in our key takeaways in the next slide. Key takeaways. First, always keep in mind that an identity matrix must always be a square matrix. This means the number of rows must be exactly equal to the number of columns. Second, as we saw in our examples, the elements located on the principal diagonal, running from the top left to the bottom right, must always be equal to 1. Third, every other element in the matrix, those that are not on the main diagonal, must be 0. In terms of notation, we denote the identity matrix of order n as I sub n. Finally, the most critical property to remember is that it acts as the multiplicative identity in matrix multiplication. Just as multiplying a real number by 1 leaves it unchanged, multiplying a square matrix by the identity matrix results in the original matrix. Now that we have covered the definitions, construction, and the relationship between different types of matrices, let us summarize the most important points to remember. Now that we have a clear summary of the rules, let us move to the final slide to discuss some common mistakes you should avoid when working with these matrices. Common mistakes to avoid. First, always remember that an identity matrix must be a square matrix. A common error is attempting to create a non-square identity matrix, for example, a 2 by 3 matrix. This is incorrect. By definition, the number of rows must equal the number of columns. Second, when filling in your matrix, ensure that the ones are placed specifically on the principal diagonal. This is the diagonal that runs from the top left corner down to the bottom right corner. Placing ones anywhere else would violate the definition we discussed earlier. Finally, be careful not to confuse the identity matrix with a scalar matrix. As we mentioned in our discussion on matrix relationships, if you use other constants, such as 2s or 5s, on the diagonal, you have created a scalar matrix, not an identity matrix. To qualify as an identity matrix, only the number 1 is permitted on the principal diagonal. Now that we have covered the definitions and examples, let us conclude by discussing some common mistakes to avoid so that you can apply these concepts accurately.